Welcome to Student Discover. We are covering Curve Sketching Volume 1 and 2. Volume 1 will include translation, scaling and generic transformation, whereas Volume 2 will include locus, directrix, eccentricity and asymptotus. Curve sketching. There are three approaches. Translation, scaling, and generic transformation. Let's go for the first one, translation. Translation is equivalent to shifting of the origin. If we can write a function or a variable xg is equal to x minus a, then our y is equal to f of x, y is equal to g of xg. If we take xg is equal to x minus a, we can rewrite x is equal to xg plus a, which means whenever we plot for x, all of the points in xg will be translated by plus a units if we apply minus a into this equation. Next, let's move on to scaling. If we have a graph of this form, and if we scale the graph by a units, then we get the graph in this form. This is compressed by a units. If we apply 1 by a here, it's expanded by 1 by a units, a units. This can be shown from the following equation. If we write xg is equal to ax, then our x, the plot, becomes xg divided by a. So when you plot g of xg, which is same as f of ax compressed by a units or scaled by a units. If we write g of xg is equal to f of x by a, then it's scaling by 1 by a units in the x direction. Let's take the third example, which is generic transformation. A generic transformation could be a rotation, a shift or translation, and scale or scaling. Can be represented in here. If this is the origin, and if we have a canvas here or a graph here, and if we shift the origin by x and y units, and rotate the graph, then our new axis will be here, rotated by theta. And if we can apply a scaling by A units, we obtain our new plot scaled by A units, rotated by theta, and translated by x0 and y0. Generic transformation can also be represented by transformation matrix, such as A is equal to 0, 1, 1, 0. When you multiply A by x, here we get 0 into x plus 1 into y, which is y, 1 into x plus 0 into y, which is x. Curve sketching, we have 4 concepts. First is locus, then directrix, eccentricity, and asymptotes. Let's move on to locus and define what exactly locus is. Locus is set of all points which are obeying a certain rule. So set of all points that obey a particular rule. We're not done with this. I'll explain what exactly and how exactly a locus is found. Let's take an example. An example is a parabola, which we all know. The equation of the parabola is y square is equal to 4ax. That's one of the examples. Consider there is a line on the left hand side of the y-axis, and we are plotting all the points which are perpendicular and equidistant from this particular fixed line towards our right hand side. So from here, if we plot an equidistant point, it's this, and here, such that these two are equal, A1 and A2. The next point will be A3, A4. Our another point will be A5 and A6. So if we join all of these points together and form a meaningful curve, then the set of points is called a locus. Now let's plot our parabola. So to plot, you have to draw a table consisting of x and y. So if our x is 0.5, which is half, 1 by 2, and already our a is 1, if we fix a as 1, then our y value will be 0.5 into 4, which is 2. So y square is 2 and y is plus or minus root 2. If x is 1, it's plus or minus 2. If x is 1.5, y is plus or minus root 6. If x is 2, y is plus or minus root 8. And so on with, if x is 4, y is plus or minus 4. So let's actually plot a parabola now. So a parabola will be, if x is 0.5, y is plus or minus root 2. So 0.5x, 1, 2, 3, 4, 1, 2, 3, 4. X is 0.5, y is plus or minus root 2. Plus or minus root 2 will be around 1.414. So that's here. X is 1, y is plus or minus 2. X is 1.5, plus or minus root 6 is around 2. So 1.5. X is 2, y is plus or minus 8, which is closer to 3. But it's not 3. X is 4, y is plus or minus 4. That will be plotted at this point. So if we connect all of these points, that will form a curve. Similarly, for all positive y, there is a negative y. So we can plot a mirror image along the x-axis for this curve, which would be something like this. And when you connect both of these together, like plot even when x is 0, y is as well 0, we get the parabola which passes through origin and a curve similar to this form. Since we have explained what a locus is, we can move on to directrix. Consider a curve of the form xy equal to 1 or y equal to 1 is positive, y is positive, x is negative, y is negative. So it's either, let's define the quadrants. It's either in the first quadrant or the third quadrant. It cannot be in the 2 and 4 quadrant. So the greater the x, smaller is the y, lesser the x, greater is the y. So a curve will be the form a directrix is defined by a fixed line which determines how the curve is generated. Thinking back to our earlier example, we generated a parabola based on equidistant points from a directrix. So let's consider there is a curve which is at 45 degrees from y-axis. For this curve, there is a focal point here and here. Hyperbola is defined by ratio between the distances from the focal point and distances from the directrix. That is ratio R1 by R2 is constant. For parabola it's equal to 1. For hyperbola it's greater than 1. So a fixed line in here, which is called the directrix, has been used to generate the hyperbola. Directrix is defined by a fixed line that generates a curve or even a geometric object onto the coordinate space. Fixed line and generates a curve. Eccentricity is defined as a ratio between the distance to the focus and distance to the directrix. So for example, R1 by R2 is equal to eccentricity E. For circle, eccentricity is 0. For ellipse, the eccentricity is less than 1. For parabola, the eccentricity is 1. For hyperbola, the eccentricity is greater than 1. Asymptote. An asymptote is a straight line that meets curve at infinity. One example is a hyperbola of the form x squared by a squared minus y squared by b squared is equal to 1, and our asymptote is y equal to mx. Our directrix would be